Alright, so hello and welcome back again. Excuse me, wanted to continue what we were doing. I don't know, I kind of laid down, took some time, but I don't know, excuse me, feel like I had some food, I laid down, I relaxed. I still feel like I feel like I should go to sleep, but I'm really tired, but it's also not time for bed at all, I guess. Like I would need to wait at least 3 hours before I go to sleep for it to be somewhat reasonable. It's like way too early to go to sleep. I end up waking up at like 4 a.m. and then what? So I guess I'll do more programming at 4 a.m. So yeah, I don't know. I'm tired, but I don't really want to go to bed either. And anything else that I could think of doing just seems kind of meaningless. So not meaningless, but like not what I want to do right now. Like what I want to do is try to solve these problems. Like that's the main thing I'm trying to do right now. Comparators are used to compare two objects. In this challenge, you'll create a comparator and use it to sort an array. The player class is provided for you in your editor. It has two fields, a name, string, and a score. We just did something like this: string, a score integer, given an array of n player objects, write a comparator that sorts them in order of decreasing score. If two or more players have the same score, sorts them in order of decreasing score. If two or more players have the same score, sort those players alphabetically by name. To do this, you must create a checker class that implements the comparator interface, then write an int compare player A, player B method implementing the comparator compare2 method. So actually, you don't necessarily need that checker class. I mean, we're going to create that, but you don't actually need it, believe it or not. Input from standard in is handled by the locked stub code in the solution class. The first line contains an integer n denoting the number of players. Each of the n subsequent lines contains a player's name and score, respectively. So sort by score descending, and then sort by name lexicographically. Okay. And ascending, like lexicographically ascending. Rather than descending. So first line contains integer n denoting the number of players. Each of the n subsequent lines contains a player's name and score respectively. Subsequent lines contains the player's name and score respectively. Two players can have the same name. Names consist of lowercase English letters. Not responsible for printing any output to standard out the lock stub code. Create an object, you can use it. Okay. Interesting. What if they have the same name? If they have the same score, then you sort by name. Obviously, if they have the same name and the same score, I guess it doesn't matter. Okay. So yeah, you don't actually need a checker class for this. You can use an anonymous. Well, I guess the way that they've set this up, you do need a checker class. But if you were to do a if you were to do this on your own in this situation, you would not necessarily, you can use an anonymous comparator class. Excuse me. Okay, so yeah, we just need one override, and that's the compare2, and that's going to give you an integer. I believe it's an integer. Arrays sort. Okay, interesting. I don't know if this is stable. If it's stable, then we could do something kind of interesting here, but if it's not, then we won't be able to do that. So we'll use player P1 to player P2, and I think you can do it this way, using generics. And we're going to say there's name and score. So P1 dot score, we want descending, right? So we want ascending would be less than, so we want this greater than. And because it's stable, you can do an interesting thing. You can use an OR here, I believe. And you can say, now you can say P1.name is less than P2.name. Yeah, this only works for stable sorts though. If it's not a stable sort, then you have to do something a little bit differently. Okay. Bad operand types. It's not override or implement a method from a supertype. Oh, okay. Fair enough. Fair enough. And these you might just need to do something like this. Parentheses. Actually, you know what? That's not what it is. That's my mistake. This is not, I did this wrong. Yeah, it's actually, I see. This is actually kind of tricky because the compare to is like a three-way comparison. So, yeah, okay. So really if P1.score is greater than, if P1.score is equal to P2.score, then you would return P1.name.compare to P2.name. Otherwise, you return this. So if the scores are equal, you want to sort of yield control to the other comparator for strings, whereas otherwise you can just use the greater than. So actually, it doesn't quite work the way I would have liked it to. I kind of forgot. You could, if this was a Boolean, then it would work okay, but this uses a three-way comparison, so it's actually a little bit more complicated. So I was trying to be clever here, but it doesn't work out like that. Checker is not abstract and does not override abstract method compare and comparator. I thought it was compare to, not compare. Okay. Whoops. Whoops. And this is going to be public. Okay. Incompatible types. Int Boolean. Oh, I see. That's fair. That's fair. Now I don't recall if it's the negative. It's a negative number or the positive number. We might not get the right sorting if we do it this way. But yeah, the three-way sorting, we need to do it this way. Return the integer properly. So now I think it's if this is less than that, then you return a -1, but we're doing sort of the inversion of that because these scores are descending, which I think is right. I think we did this correctly, it seems. Yeah, Amy and David, it's going to be actually, you don't need this. this is what ends up being. Okay. So if we reverse these two, that'll give us an ascending scores, which is wrong. So we did get that correct. Okay. Just wanted to test that to make sure that that works properly. All right, let's see how we do. Nice. Okay, keep going. Yeah, I mean, yeah, again, you can use an anonymous comparator and also, unfortunately, a three-way comparison. It's not as terse, I guess. A stable sort with only a Boolean comparator, though, you can actually use. You can actually kind of like chain with or logical ORs across your conditions, which is kind of neat. Makes things a lot more compact and terse. It's kind of a nuanced thing, but yeah, definitely something I like, something I appreciate. You are given a list of student information, ID, first name, and CGPA. Your task is to rearrange them according to their CGPA in decreasing order. If two students have the same CGPA, then arrange them according to their first name in alphabetical order. If those two students also have the same first name, then order them according to their ID. No two students have the same ID. You can use comparators to sort a list of objects. See the Oracle docs to learn about comparators. First line of input contains an integer n representing the total number of students. The next n lines contain a list of student information in the following structure: ID, name, CGPA. I guess CGPA is like current GPA. I'm not sure what that means exactly. The C is. The name contains only lowercase English letters. The ID contains only integer numbers without leading zeros. The CGPA will contain at most 2 digits after the decimal point. So there's 1,000 students, there's an ID number, there's a name, and there's a GPA. Okay. Excuse me, after rearranging the students according to the above rules, print the first name of each student on a separate line. Okay, so we are sample input, sample output. So I guess it's, what's the order that they want? Sort? Okay, so we want according to their CGPA in decreasing order. So decreasing order on the CGPA. But if they have the same CGPA, arrange them according to their first name in alphabetical order. So increasing in alphabetical order. Yeah, so descending GPA, ascending alphabetical order, and if they have the same first name, so they have the same GPA, the same first name, then order them according to their ID. And then it's an ascending order with respect to ID. Okay, interesting. So yeah, we're going to use a comparator here. Full screen layout. Oh, that's better. That's a lot better. Okay. So what is, can I, okay. That's all right. I want to, what does this do? Reset code, okay. Student, test cases, get the name, get the GPA, get the D name, student, okay. So what are they looking for? So complete the code, okay. Okay, so we're just gonna sort the, all right, fair enough. So collections, and what kind of a list is this? It's an array list, right? Yeah, student list. So collections sort, student list, and then we're gonna have a new comparator of students. And we're going to, so we're going to have an anonymous class, a new instance of the anonymous class. It's going to override our compare function, and that's going to just be between two students, student 1, student 2, or just student A, student B. Let's probably do it that way. And then, so we say if a.cgpa is greater than b.cgpa, then return 1. So we want else if, so it's less than b.cgpa. Okay, so what we're looking for is, how do we do this? A.cgpa and B.cgpa. What we're looking for is, oh, there's getters and setters over here too. These are private. Okay. So get CGPA we need to use. All right. I have to think about this for a moment. Okay, so student A, student B. If A is greater than B, now is that it should be a negative number or positive number? No, we said we want this in decreasing order. We just did this, but how do we remember this in general? Well, if A is less than B, you want it to be negative. But if we're doing things in the other direction, then you actually want to do it this way. Yeah, if you want to be if you want ascending, then A less than B would be negative. If you want descending, it's the other way around. Yeah, so you can do that, and then otherwise, if they're equal, then you could just do 3 blocks of the same thing. So the next one is the compare to for the names. Finally, it's the IDs, but the name is the last thing. So if they're not equal to each other, the names, so a dot get fname, which is capital F name, is not if dot equals b dot get name f name. So if these are equal to each other, then you're going to do the next round, which is the IDs, get ID, and that's going to be sorted in ascending order. So we can do, so really I should do it this way. I should A less than is positive, and then greater than is negative. And if they're equal, then we check the name. If the name is equal, then we're going to use the ID. And ascending, and yeah, also ascending rather than descending for the names. And then otherwise return a dot get f name compare to b dot get f name. Okay, let's try these things, see how this goes. Oh, didn't realize it. Okay, cannot find symbol. Cannot find symbol, really? Get CGPA? Wouldn't this be here? Oh, I see. Okay. And I think the other ones have issues too, right? Get ID, yeah, that one also is an issue. One of the reasons I like to use private classes for things is that I don't need to worry about all those getters and setters and things like that. I can just make all the, or local classes maybe. Yeah, I guess inner classes, they probably would be local classes or inner classes, is because all those variables, you don't need to make them private. You can make them all public because you're in a local context. You wouldn't be able to access that context outside of the, I think typically you wouldn't be able to access that context outside of, wouldn't be able to access those variables outside of that context anyway. Excuse me. So, although I could be wrong about that. I think you can in some instances, like you can, basically it would be sort of this class would be sort of inside this namespace. And so in theory you could actually access it. But anyway, not that big of a deal, but it's kind of annoying having to, use those getters and setters. Okay, so, right. I mean, we basically have seen this a few times already today. So this is not that interesting. This was not that interesting, that question. Okay, computer science, a double-ended queue, DEC, often abbreviated as a DEC, pronounced DEC, is an abstract data type that generalizes a queue for which elements can be added to or removed from either the front head or back tail. DEC interfaces can be implemented using various types of collections such as linked list or double array DEC classes. For example, DEC can be declared as DEC equals new linked list or DEC equals new array DEC. You can find more details about DEC here. In this problem, you are given n integers. You need to find the, that's interesting. I don't know much about the array DEC. It's curious. Really? Have a DEC that's an array. Huh. Given n integers, you need to find the maximum number of unique integers among all the possible contiguous subarrays of size m. You need to find the maximum number of unique integers among all the possible contiguous subarrays of size m. In this problem, you are given n integers. You need to find the maximum number of unique integers among all the possible contiguous subarrays of size n. You are given n integers. You need to find the maximum number of unique integers among all the possible contiguous subarrays of size m. N integers. Time limit is 3 seconds for this problem. Okay. For a moment there, I thought, wait a minute, it'd take me 3 seconds, more than 3 seconds just to read this and comprehend this. 3 second limit for how much time you could take for the code to execute on test cases. Got it. N integers, you need to find the maximum number of unique integers among all the possible contiguous subarrays of size m. Interesting. But wouldn't that just be, why wouldn't you just take, are these subarray sums? Or, oh, I see. I think I understand. Of all the contiguous subarrays of that particular size. Right, in other words, okay, I was going to say you can just take the maximum number of unique integers across across the array. Okay, I think I understand. All right. Whew. Okay. First line gives you two integers n and m, representing total number of integers and the size of the subarray. The next n lines are space separated integers. Okay, that's fine. So, yeah. Numbers range between 0 and a billion, I think is what that is. And these are between 100,000. Alright, n is 100,000. Maximum number of unique integers among all possible contiguous subarrays of size m. Okay, I think I get it. A few things to say about this. It's not a particularly hard question. I can see why they're suggesting to use a deck. I think I get it. That's not a bad idea. It's definitely an more efficient way to do it. Or I shouldn't say more efficient. More efficient. That's a more efficient way to do it. A few things to note. So you can. I think I know the solution to this problem. So you can. Just thinking here. You can. There was something I wanted to say about this question. I think I got. What I wanted to say was, if it was all subarrays of any size, then the maximum number of unique integers you could just run through the largest subarray, right? Because the more numbers can only make that number the number of unique value integers increase if you add more numbers to your subarray. So the optimal would always be just the total number of unique integers among the whole array. However, this question is kind of special. They're saying you're only considering these particular subarrays of a particular size. And so you can do this in O of n times m time. There are roughly O of n of these subarrays, and then you could just process each subarray directly, right? And that would take m time per subarray. However, what they're suggesting to use a deck is that you can actually say, okay, I'm going to maintain this deck, and you can use a set also for the m elements that are currently in the deck. So initialize the deck with the first m elements, initialize the set with the first m elements, and then you can move sort of one element at a time to the right, and say you're going to add this next element. You should remove first, I think. So you remove and now here's the tricky thing too, is that you've got to be careful. You want to use a set, but actually it might be better to use a frequency map. It's probably better than to use a set. So I would suggest use a hash map in the form of a frequency map rather than a hash set. And the reason is that you would probably want to count the duplicates for each number. So if there's only one number, the frequency will be 1. If you have more than one number, when you remove, so you're going to remove the leftmost element of your sort of subarray, of your contiguous subarray, and then decrement the frequency of your frequency map, which if the frequency map has a 0, then you can remove that key altogether, right? And if the frequencies become 0, you can remove the key altogether. And then you're going to add the next element to your frequency map and also to the deck on the right side of m. So the m plus 1 element. So the first element and the m plus 1 element. And you can loop through all the elements that way, loop through all the indices that way, and sort of maintain this window. And your frequency, each time you can count the size after you've removed and added to your frequency map, you can count the number of pairs in the frequency map, or the size of the hash map, and that'll give you the size of each of these. What do they call that? Each of these contiguous subarray sums, or the number of unique integers for each contiguous subarray sum. And then each time you do that, you can just take the size and check if that's larger than what your current maximum is, and then update your current maximum. So this is a relatively easy question, I would say, overall. I don't know what ranking they gave this. Did they give it a ranking? Is there a way to know? If this is an easy or hard or medium or whatever it is. Let's go back to full screen. Medium. Okay, yes. I would say it's medium. Yeah, it's not so easy that you would like immediately solve it or something, but it's easy enough where you could do that, like as we basically just did. Let's use a. I mean, like this is fine. Array deck is fine. Doesn't really matter. Can use a new. Let's use array deck. Let's do that. I like that. Okay. Oh, it's already there. Okay. So num equals in next int, and we're gonna say we're gonna use a hash map as well. So our hash map we want to use hash map of integers, and we call this the frequency is new hash map integers, and we have our array deck, and what we're going to do is say if size deck.size is less than m, then we're going to should we push back, we'll say something like that. We'll look up the syntax in a moment. Push back num, and we're also going to say it's frequency of num plus plus. All right, I think it's always initially 0, and if that works, hopefully that works. And then we may have to update the syntax there. Now, otherwise, if we are m, then what we're going to do is can actually int val equals, since this is an array deck, you can actually grab the this first value. So yeah, well, we can do deck. Actually, you don't even need to do it that way. You can just do the front. So deck front is the value, and we're going to say frequency of value minus minus. Say if frequency of value equals 0, then we're going to remove dot remove value altogether. Again, I have to check the syntax on these things. And then we're going to take the number, and we're going to add frequency of num plus plus, and then we're going to take our ret, we'll call it initially 0, and say if ret is less than frequency.size, or hash map size, then ret is equal to frequency. Set it to that hash map size. And that's about it, really. And then finally, I think we just print it, right? That's what they want. So we just print ret at the end of this. What do we get? Let's see if this, I have to check the syntax for this, certainly. Oh, right, 2 integers. Okay. Oh, man. Add last, add first, get last, get first. Okay. Peak first, peak last. All right, so we want add last. Oh yes, frequency num. We'll need to take a look at that in a moment. The deck get front. And And actually, it seems you add last no matter what. Can also do this at every step as well. So really, if you're greater than or equal to m, then you're going to pop from the front and decrement your frequency map first. Yeah, that's kind of where it comes down to. So these two items, though, are a question. Right, I think the compiler is giving me, is questioning me here. Cannot find symbol, get front. Really? Oh, it's probably, excuse me. Need that wrapper. What do you mean? First, not front. First. Let's see. Okay. Incompatible types. Okay. These are just integers. All right. So Java hash map. Let's take a look at that. See what the syntax looks like. Contains clear clone compute. Oh, that's interesting. Compute a mapping for the specified key and its current map value. Huh. Interesting. I don't really understand what that does, what these do. Compute of absent, compute of present, get or default is empty, key set, merge, put, remove, replace. Okay. So I guess we'll do getter default. We can do getter default and put for the increment, and we would say your current amount is going to be frequency dot get val, and then we're going to say frequency. Really should be an update that we're going to do. Yeah, replace. Now, yeah, so replace key, which is val, with current amount, -1. And then if, well, yeah. becomes a little bit more reasonable to do it this way. So you say if current amount minus 1 equals 0, or current amount equals 0, or equals 1, then we remove it all together. Otherwise we replace the current amount minus 1. Okay. Or we'll say new amount. How about that? That's better. If the new amount is 0, remove it. Otherwise somehow we can do less than or equal to 0. Still remove it. Okay, and now here we have integer new amount is going to be frequency get or default of num 0 plus 1, and then set if that contains, or if new amount is greater than 1. If the new amount is greater than 1, then we're going to frequency.replace num with the new amount. Otherwise, frequency put initially num 1 or new amount. Yes, something like this. Let's see if that compiles. Start with that. No. Can I find symbol frequency? It's right here. Replace integer, variable frequency of type. Replace integer, variable frequency of type integer. Oh. What do you mean? What? It's right here. What do you mean? Is this too... Oh, it's Java 7 instead of Java 8. Oh, I see. Alright, let's go to 7 then. Maybe that's why. I see. I see. Maybe just put... Contains key. Okay, so we don't have replace available. Do we have remove? We do. I think it's just put then. I think in any case we remove. And then put back. So as long as the new amount is greater than 0, then we'll put this val. And then we can say there's no default, right? So we can say if frequency dot contains num, new amount is going to be equal to frequency dot get num plus 1. And we would say frequency dot remove num, put num new amount. Otherwise, we'll say frequency put num 1. Something like this should be fine, I think. Might be able to clean this up a bit. Cannot find symbol. Int. Well, can't you? I mean, you can do this too. Make it simple. Use the wrapper. Okay. That would make sense then. We don't have contains either. We had. I thought we had contains key. Okay, sure. Sure. What happens here? Runtime error. Whoa. Okay. Wasn't expecting that at all, but that's fine. Oh, we need to check here too. If we contain this key, then we can say integer new amount is equal to frequency get val -1, and then which it should always, I mean, it basically is always there. It's got to be there. Yeah, we actually don't need this check, but that's okay. So we remove this, and if it's greater than 0, then we'll put it back with the new amount. How did we get a runtime error? I was not expecting that. What? Cannot find symbol new amount. Why is that the case? Oh. Don't need this part anymore. Oh. What? Wait a second, what? How did... Let's back up. Why did this... That's not correct. This shouldn't matter, right? So we get the next number. So deck size is greater than or equal to m. Could say to the last number. Then it's true. We get the first integer. Now the frequency map is always going to have that number in there. At least one of them. It must. So then we get our new amount, we remove that value, and then we put in the frequency map. If it's greater than 1, then we update. And then we add here. This should not be an issue. When does that happen, really? Now, I added this part. For some reason this made a difference. So if we run that. I think Java is kind of interesting because no, I think it's fine. I think this will work. I was gonna say I think Java has issues with white space, but that's not true. So this shouldn't matter. You shouldn't actually need this part. And I'm very curious as to why. Excuse me. So I'll print the value and print I when that happens. 5, 5. 0, 1, 2, 3, 4, 5. Yeah, that's exactly what I was thinking. That is exactly what I was thinking. Now we form our deck. The first, I guess what you're saying here is that in our frequency map we don't have a 5. No, that's just not true. Six and 3. 5, 2, 3. Yeah. So 5 is the first. I is 5. 0, 1, 2, 3, 4, 5. So what's the issue? So somehow we get a null pointer. I think it's this gives you a null pointer. We don't get the frequency there of 5. But that's wrong because that should have a 1 there. That is very confusing. That is very confusing. Maybe this should be an integer. Maybe that does make a difference. No. Fall asleep over here. Okay, let's try this. Let's try this and see what happens. Can't iterate over the hashmap. Excuse me, really? That's annoying. Really? Can we not, excuse me. There we go. Collection view of the values contained in this map. Clone. No. A set view. Entry set. Yeah, it's excuse me. Oh boy. Falling asleep over here. Falling asleep. I want to. I think I get the set view of what's in here. Yeah, the entry set, and then loop over the entry set. I think that's what we're looking to do here. Yeah, actually, this is really wrong. This is not how that works because it's a frequency map, right? Not a I wish I could use auto with it's a map.entry. Map.entry of integer. Yeah, that's actually what we're supposed to have here. It's a, yeah, right, again, frequency map. So you're gonna have value key is X. Excuse me. Get key plus value key value. Which I don't think that's going to work the way that I would like it to, by the way. Oh, okay, it works. Sweet. Oh boy. Excuse me. So in each case, it's there, right? So key 3, value 1, key 5, value 2. So there's 355 is here. That's the first time. Next time becomes you remove that 5 and you push a 2. And then the next thing, you have 352. So 2 as a 1, 3 as a 1, 5 as a 1. You pop that 3, push this 3. Should have the same thing again. But here, you don't pop the, so 352. Now that's really interesting. For some reason here, you pop the 3 and then push back the 3. You should still have the 5. For some reason you pop a 5. Why did that happen? What? Oh, I must have mixed up val and num. That must be it. No. It's not what happened. There's just num here, which is correct. And, oh, yeah, no, we're updating the frequency map accordingly. Updating the deck and the frequency map. So frequency contains key num. Excuse me. Uh, 5, 3, 5, right? Pop 5, push 2, 3, 5, 2, pop 3, push 3. Shouldn't be 5 that we're popping. Is that what happened? Somehow oh, is that why? It's adding first and adding last incorrectly. Add last, get first. This is so confusing. This is very confusing. Why is this happening? Why is it removing a 5? What? What? Oh. No, that's fine. Oh, no. That's so confusing. So confusing. This could be added at the very end. This doesn't need to be. What? Excuse me. What is going on? I don't know. Something strange is going on. I don't know what it is. Something strange in the neighborhood. Something strange in the neighborhood. Ghostbusters. Ghostbusters. Back of deck, back of deck, back of deck, front of deck. 3, 5, 2. Back of deck 2. So you pop a 5. You have a 3, 1, 2 now. Back of deck 2. Front of deck is 5. 2, 3, 5 now. Pushing on the 5. Well, my question is, oh, actually, this is before we pop. Oh, that might be why. I see the problem. That is a very subtle thing. So when your deck size is greater than or equal to M, actually this is incorrect, right? This is confusing. It shouldn't. I don't know. This is so confusing. I don't know. So, I don't know. I'm confused. We'll just say I'm confused. So here we pop the front of the deck. 5. So there's 3, 1, yeah, 5 through 5. That's fine. Pop the front of the deck. Have a back of the deck 2. We push that on. Right. This gets updated to 5, 3, 3, 1, 5, 1. Then we have 2, 1, 3, 1, 5, 1. Then the front has a 5. We remove that. Then we have 2, 1, 3, 1, 2, 1, 3, 2, and then somehow we see 5 again. Why is the front of the deck 5 again? Five, 3, 5. Front is 5. Get the front is 5 3 times in a row. Get first. Oh, that's why. Oh, I really misread. Okay. You need to remove first. Oh, okay, that's why I'm so confused. Of course. So the get first and the get first and the peek first are basically the same function, and that was why I was so confused. Is because I thought let's give it a shot. I thought that okay, that was like I don't know 10-15 minutes ago on that. I had made a pretty reasonable assumption that they wouldn't have the same function do the same thing. One function, two different functions do exactly the same thing. The get first and the peek first are almost exactly the same. Retrieves but does not remove the first element. Retrieves but does not remove the first element, or returns null, which is it's not the same thing. But I assume the difference between these two is actually the removal, and I thought, oh, okay, sure. But that was not correct. Okay. I guess you throw an exception if there is no first to get here, whereas peek doesn't throw an exception, just returns null. I'm gonna go lay down and take a nap again. So it's supposed to be remove first. Oh man, that was so much extra work for really nothing. Now this removing and putting, I suppose this is fine. Yeah, because we want to keep the size of the hash map kind of set correctly. If we didn't remove the ones that were 0, then we'd have to calculate the size by counting all the values that aren't 0, which is actually really expensive because the size is updated automatically, and whereas the number of things that have zeros, we'd have to keep track of that too, and simultaneously, so it's easier to just remove it altogether. And then what else do we have? We have yeah, I mean, this is fine, you know. Doesn't have the key, add it if it does. I mean, there are other routines you can use to do this. But the get, I don't think get works properly if you don't have. Let's see what happens if you try to get something that's not there, or null. That's interesting. So you can just get, I think, without it. Yeah, you can do this, I think. Now, my question is, can you put will it overwrite the previous key? I think it does. I don't know. Let's see what happens if we do this. Runtime errors. Oh, that's interesting. Null pointer exception. So you can't add. Really? Huh. Can you do the rest of this back. Oh, okay, you can't add one. Interesting. Oh. Yeah, you can't add one if you can't add one to a null pointer, to the null object. It's really a null object because they don't have pointers in Java. You have references only. Also, look at this gigantic cursor. Okay. Anyway, we can move on to the next thing here. So, how much time we have here? Yeah, an hour or so we spent. I'm able to spend another hour, and then I guess go to sleep. Java's bitset class implements a vector of bit values, 0, 1, that grow as needed, allowing us to easily manipulate bits while optimizing space when compared to other collections. Any element having a bit value of 1 is called the set bit. Given two bit sets, B1 and B2 of size n, where all bits in both bit sets are initialized to 0. Perform a series of m operations. After each operation, print the number of set bits in the respective bit sets as two space-separated integers on a new line. First line contains two space-separated integers n, the length of both bit sets b1 and b2, and m, the number of operations to perform respectively. The m subsequent lines each contain an operation in one of the following forms: and, or, XOR, flip, set, 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 index, set, index. In the list above, set is the integer 1 or 2, where 1 denotes b1 and 2 denotes b2. Index is an integer denoting a bit's index in the bit set corresponding to set. For the binary operations and, or, and XOR, operands are read from left to right, and the bit set resulting from the operation replaces the contents of the first operand. For example, and 2, 1 is the b2 is the left operand, and b1 is the right operand. This operation should assign the result of b2 and b1 to b2. Oh, okay. Replace the contents of the first operand. Alright, that's kind of interesting. So, constraints, there's 1,000 is n, and 10,000 is m. I think n being 1,000 is the length of the bit sets, and 10,000 are the number of operations that you're going to perform. After each operation, print the respective number of set bits. In bit set b1 and bit set b2 is two space-separated integers on a new line. So 5, 4, and 1 and 2, set 1, 4, flip 2, 2, or 2, 1, sample output. So they're initially 0 bits after you AND them, so 1, 2, 3, 4, right? So there's 0 bits set 1, 4, there's 1 bit set in the first vector, or rather the first one, b1 has 1 bit, that's 4. Flip 2, 2, so in the second, what does flip do? Oh, flips the bit for number 2. So then now there's 1 and 1, and then when you OR 2 and 1, replace 2 with that, then you should have the second bit set gets replaced with the OR of both bit sets, which it has. So the second one should have 2. Flipped. Okay. Oh, that is so confusing. Initially, n is 5, m is 4, b1, b2. Print the respective number of set bits in b1 as a pair of space-separated integers on a new line. And they explain each of these things. Okay. Oh man, this isn't easy? This is a nuisance. Well, it's kind of inefficient to do this because 1,000 by 10,000 is like 10 million. So I guess it's. I mean, I guess it's okay. We just perform the operations. Really, it's pretty much what we're doing. It's sort of like a state machine type of thing. The thing that's really tricky. Oh man, dude, I want to go lay down. I just want to lay down. It's just annoying. This is I mean, it's okay. It is what it is, I guess. But yeah, we're sort of just processing each. Oh boy. Okay. Oh. Excuse me. Oh, ready to take a nap. Ready for bed. So, what I'm thinking is, I think we're going to do that approach, right? The 10, 20 million operations type of thing. I think it'll be relatively efficient, even though it's a lot of operations because we're using the bit sets. Excuse me. Thing that I'm pondering is well, when you parse each line, you've got to convert that to sort of like a command. It really could just be a switch statement, and then kind of a function that we call. Implement each of these functions. I think there's 6 of them, and yeah, I mean, I think just directly implementing each of these functions should be fine. One of the questions is about each of these bit sets. How many bits are set to 1 after each iteration? And since after each command, and I guess since each command, well, yeah, I mean, I guess it's as simple as just keeping track of the count and returning the count at the end. So when you perform an OR, you perform an OR on every bit in the bit set, right? So every index from right to left, or left to right, however you want to look at it, and then every time you see a 1, you just keep track of that. And same thing you do with XOR, and same thing you do with the AND, the OR, the XOR, and the AND. Yeah, you can just, in each of these cases, you can just keep track of the count of bits that are flipped on. And that's fine, just return that when you're done. Although, yeah, right, the bit sets that you're operating on, they're all references, so you can update them directly. Yeah, that's fine. That is fine. Interesting. Interesting. Hmm. I'm very tired, if you don't mind. Don't mind me laying down for a moment here. Yeah, this problem isn't too bad, I guess. I guess it is an easy one. Relatively speaking, it's a lot of extra, it's sort of, not a lot, it's a little bit of extra coding, I suppose. But yeah, I mean, overall, it is actually relatively easy. I wouldn't say it's a hard problem. In terms of theory, it's pretty easy. One reason I was thinking maybe this would be a little bit harder is because of the what is it? It could be a little bit harder because of the thinking here. Right, the amount of operations that need to be done. Doing 1,000 operations per execution is expensive, right? You have 1,000 times 10,000. I think because we're doing binary operations, it's like bit operations instead of, so integers normally would have 32 bits that we're operating on. We're actually doing, it's almost as if we're doing 32 times less work. So it's as if you took that ultimate number that we're executing on, dividing by 32. It's maybe the way to think about it, which would be fine, I suppose. I guess it would be, yeah, we could, I mean, I don't actually know. I think that's reasonable. As I said, I'm not sure because we're, just that loop of looping over 1,000 of these indices, of these bits, we run into an issue of adding 1,000 times, right, as we increment our loop. So I'm really not sure ultimately if this is going to be a reasonable runtime. I think it'll be okay though. I think it'll be fine. I also think the time limit that we get for each of these problems is quite gratuitous for the most part. Yeah, I think you get like a few seconds usually. So I don't actually know though. I mean, oh, I need to charge the headset. Yeah, I've noticed that LeetCode seems to be pretty like reasonable in terms of how much time you have with regard to like the problem. Yeah, I think LeetCode is usually pretty good about giving you enough time, even though it looks like the problem size seems to be pretty big, I guess. So yeah, we'll try this. We'll see how this goes. I think it'll be okay. I also got to charge the headset, so you're going to start hearing noises now, because you're going to start hearing noises now because the headset is charging. You're going to have like a small buzzing noise, I think, now. So, okay. So, let's do this then. Let's parse this. So, the first thing we're going to do, 5, 4, okay. So, excuse me. Okay. Private int. This is going to be set size. And then we're going to have That's there's M and N we said, right? So N is the set size, M is the number of commands, operations. So we can say scanner, new scanner of system.in. We can say int, or we can just say set size, sc.nextInt. We can say int num operations, sc.nextInt. We can say for int I equals 0, I is less than num operations. We're going to, so we're going to say string opcode. It's going to be sc next. And we're going to say int left bitset sc nextInt. Right bitset, and we're going to say I don't know, something like this. So we say switch on the opcode. Let's say case. We have each of these cases. 1, 2, 3, 4, 5. It's actually not. It's actually not. It's going to be op1, op2. Yeah. Okay, so we have AND or XOR flip and set. And then default doesn't do anything. Don't actually need default. Actually, I don't know if that's true. You might need it. Okay, AND or XOR flip set. So we have two different operations. We're going to say the AND, private static AND operation. So I think we'll put the bit sets up here, I suppose. So what do they say? Oh, look at that. Oh, that's interesting. Oh, wow. You can actually use the bit sets. Oh. Whoa. Okay. Huh. The cardinality. Oh, wow. So actually these bit sets are already, oh, didn't mean to click that. These bit sets are already implemented, more or less. So that's really interesting. Huh. Oh. Oh, okay. So actually you don't need this at all. It can be right here. we could say, so there's just Java bit set. Okay, our B1 is going to be new bit set of set size. I think they're both initially 0. Let me see. Yeah, we should clear both of these initially. They probably already have bits set to initially cleared, but just to be certain. Okay, yeah, all right. It says it clearly. They're already set to false. All right. Well, in that case, we don't actually need to do. We can just write the code right here then, I think. So we're going to say the operations. So we can put these into an array, I think. Yeah, I kind of prefer that. So let's do bit set array, bit sets. And now this way we can do just array B. 0 is this new bit set, array B of 1. And now our operations, the integers, we can just subtract 1 and we know which one we're referring to. So the AND is going to be array of B of, so op1, and we could do -1 for both of them. Well, yeah, op1, -1. So the left side is going to be array B of op1 -1 and array B of op2 -1. And there's an AND function where okay. I guess the result gets stored in the one on the left. So actually in that case you just literally just AND array B of op2 -1. I think it's that simple. Right, the result is placed in, and they also wanted us to print. It's going to be array B 0 dot cardinality int a B A, B, okay. Alrighty, so let's AND, OR is the same thing, XOR is XOR, and you can even go so far as to just put these directly in there. I think part of the issue is, yeah, that should be fine. Yeah, let's do it that way. I prefer that. I don't know if it's much better. It's 2 lines instead of 3 lines. Actually, no, we'll go back. It's probably better to do it the the way I had it. It's a little bit cleaner. Okay. And now flip is going to be array B of op1 minus 1. And we're going to flip. And the index is exactly the value there. So where's the flip? Yeah, just sets the, yeah, okay, that's simple. Flip op2. And then here it's just the same thing. Array op1, set. I think set sets it to true. And I think that's it in each case, right? I get the cardinality. We can write a small routine that's just private static print cardinality. And this is going to be bit set sets. Or array B is fine, yeah. We do the same thing. Just do exactly the same thing. We know the size is 2, so that's fine. Yeah, I guess that's okay. I don't typically like this is not code that I would prefer, the one that I have here where I have this written, you know, this print cardinality function written so many times this way. I think for something like this, I'm not really sure what I would do normally. Like this is actually an example where I would really prefer to have a lambda function inside of this function, like not even have this function available to the other parts of the class itself. Maybe it's a good idea to have like a class and just have make the class like a functor kind of a thing. I don't really like that though. I kind of like, this is a thing that I would prefer in C++. I would want to do it. I would basically write like a small lambda function and then call the lambda a few times. In Java, I don't know. I probably would still do this, just make it private. I wouldn't even want to be able to call this outside of this method though, but that's okay. I mean, you're kind of somewhat, in that sense, you're somewhat limited in Java, I guess. So. In this particular very specific use case, oh, we got it. Okay, probably correct. Hey, nice. Okay. So, I probably want to stop for today. Just even though I really could keep going for like another hour or so, I think I'm okay. I think I'm done for the day. So we did okay. I don't know how much we did today. Not too much. We got like 10 questions or something. I think we started at like 24, 25. I forgot what it was. But that's okay. It's good. But yeah, this is definitely made easier with the built-in and an OR functions. And yeah, I guess that was the point of this. Okay, so I see why this is considered easy. This would be a lot more effort if this was not, if the bit sets didn't already have these built in. Yeah, that's what I was getting prepared to do. I was like, oh man, we're gonna build these these arrays for, not the bit set array, but the arrays for the like a vector of booleans is basically what I was thinking. That's kind of what you would do in C++. You do have bit sets also in C++, but it's a little bit different. But yeah, so interesting. Yeah, C++ bit sets are quite a bit different. I'll just say, yeah, quite a bit different. quite a bit different. Thinking here. Yeah, it would be very different, these routines, if you didn't have this bit set data structure already pre-built, pre-specified. You would need to do, you'd probably there probably would just be a like a function you call here, as I said, with these two operations, and then you'd have probably create a new vector, and then you do bitwise, bit by bit, perform your operations. And I was thinking, yeah, you would both count and get the cardinality, count the cardinality while you perform your operation, and also return the new. You set this. You use references and set the whatever op 1 was referring to. Set that equal to your sort of result that you just built, and have a function that does that. And then you can. I was actually thinking to return the cardinality right there too, as part of the routine. So it's kind of fun. I think it's doable with like a vector of booleans, basically, or an array list of booleans, but it's definitely computationally expensive, I think. That was the other thing I was kind of concerned about. I guess there must be some kind of optimization that's being done to do these a little bit more efficiently. I really don't know though, ultimately. But yeah, it seems to be fast enough, so that's good. So yeah, sweet. I don't know. Yeah, I kind of want to stop here. I don't know if I want to read the next problem. Did pretty good today. We got a few hours in. Got some time in. Not a heck of a lot of time, but some time. Worked on some problems. I don't know. My stamina today is kind of low. For what reason? I don't know. I guess I just didn't get a lot of sleep last night. Java priority queue. Oh, priority queues are interesting. Priority queues are like heaps, typically. They're really called heaps. They're not. Priority queue is like a very misleading name in my opinion. I think heap is a lot better. The idea with a heap is that things are organized in such a way where like a min heap, the way that it's organized, it's like a tree structure where all the children for any particular node are, if it's a min heap, they would all be larger. If it's a max heap, they're all smaller. So the largest element for a max heap would be on top, or the smallest element for a min heap would be on top. So let's say if you're dealing with a min heap, there's no relationship between the two sort of the left subtree and the right subtree, which are both heaps necessarily. They're all both min heaps. All you need to know is that the the element on top, the parent, the root, is smaller than the root of the two subtrees, the left and right subtrees, for a min heap. And that's it. That's the only property that a heap has to have. And so when you pop the element from the heap, you take the head node out, and then you replace it with the next smallest element. So the smaller of the two nodes become the head node, and the heap gets rearranged to maintain its heap structure. And it takes to pop from a heap and to to move elements such that the heap property is maintained. It's logarithmic time in general, in most implementations, typical implementations, the optimal would be how that was typically set up would be logarithmic time to remove an element, remove the minimum element, and reassert the or to readdress or to restructure the heap, so that way it maintains its heap invariant. Yeah, restructure and maintain the heap invariant would be logarithmic time usually, and then obviously if you popped all the elements, it would be n log n time, right? There's such a thing as heap sort, so where you actually create the heap and then sort by popping all the elements off the heap. The other approach is, the other detail is that it usually takes linear time to build a heap, which is interesting, depending on how you build it. If you do it in a way that's clever, you can actually build your heap in linear time rather than n log n time, which is neat. yeah, that's it. So that's, inserting elements into the heap also would be typically logarithmic time. A lot of times, actually, the heap itself will be implemented inside of an array rather than a tree. And so for that reason, you may be amortized logarithmic time to insert an element, because if it's in an array, then you may need to dynamically reallocate the size of the array. So it wouldn't be amortized constant, it would be amortized logarithmic. Logarithmic when you're not resizing, and linear when you are resizing. So yeah, so that's heaps. And priority queues basically are typically implemented by heaps. They have sort of the same idea in mind, I guess, something like that. Priority queues in an abstract data type, where it's just like a regular queue, but where additionally each element has a priority associated with it in a priority queue. An element with high priority is served before an element with low priority. Yeah, that's super confusing. I don't think it makes a lot of sense. Like, in my opinion, a priority queue and a queue are just totally different. Like, just everything about it's completely different. Because pushing things into a heap, yeah, it's just the whole thing is different. Like the whole, in my opinion, I don't think they should. I think it's something of a misnomer to call priority queues and queues to even relate them at all. I realize queues are such simple structures in the first place that you could, kind of think of a priority queue as a queue, or think of a heap as a queue, or whatever you want to call priority queue. But I think realistically, if you think about like how these two data structures are implemented, they're totally different. Like they're just completely different. Like a queue is just a linked list that you push in the front and pop from the back, whereas a priority queue is a heap, which is a tree structure, which is just completely different. And if you try to manipulate a linked list in such a way that you could somehow have priority over the elements that get popped when you pop from the back, it just doesn't make any sense. Like you just end up in a situation where you're trying to envision like just a data structure that can't be implemented using a linked list realistically. I don't think so. I guess in theory you could, because you could use a linked list to you can use a linked list like structure in an array to create like an array list, and then you'd have and then you can put your tree in the array, but like this is way too many. Ultimately you end up with a tree. Ultimately, you end up with a heap in a tree, and then can be implemented in an array, and then that can be related to a linked list, in some sense, but not really. Not really. You don't really use a linked list, and arrays are like very, very different from each other. So yeah, I really don't like that priority queues are called queues at all, because their implementation is not linked lists. Like they're so far from how queues would be implemented that it's just kind of, in my opinion, kind of inappropriate. But yet that is what people say, that they call them queues, but they're kind of not. They're really not, in my opinion. They're entirely different idea. And yeah. So anyway, like the order that things are popped from a heap is completely different from the order that it's placed in the heap, and that's it. That's kind of it. All right. Anyway, I'm gonna go. Thank you for watching. I will talk to you soon. And yeah, we'll pick things up. I think what I'm gonna do is, what am I gonna do? Probably just to stop here, relax for an hour, and then go to bed, something like that. Just watch something on YouTube, hang out, maybe go to bed sooner. I don't know. Tempted to go to bed sooner. Been yawning a lot and tired. And then we'll pick up tomorrow. We didn't get 10 hours in, but we got a few hours. We got some time. Yeah, a few hours of working on things, thinking about things. But yeah, okay. All right. Talk to you soon. Take care. Bye.